All right, so this is the lesson on 8.5, series circuits. So the do not question says, well, describe the differences that you see here in the circuit that's called a series circuit, and the other circuit that's called a parallel circuit. Well, you'll see right away that if I disconnect a light bulb from a series circuit, the rest of the circuit stops functioning, right? And in a parallel circuit, well, if I just remove one light bulb, the other light bulbs still function. But again, why is that, right? Well, why is there that difference? Well, let's take a look here in the simulation. Hold on. So you'll see here that, well, all my electrons are kind of in one path, right? On the left circuit right here, that's a series circuit. So on the left on the side, you see um, light bulbs, right? So here though, here, if I disconnect one of these light bulbs, what you'll see happen is that, well, now my switch is, well, now my electrons stop flowing, right? There's no flow anymore because now I've cut the only path for electrons to go. But if I connect it again, we'll now have electrons flowing. Now you see on the right-hand side, the right-hand circuit, well, if I cut the middle light bulb, the electrons are still flowing through the wire here, right? So there's still flow of electrons. So even though that one path is cut, the other two paths still carry electrons. And most of the things in the real world really use parallel circuits, right? And if you kind of think about it in class, well, in class, I'm sure at some point in your life you've seen the lights at the top of the classroom. One section of that of it was broken, right? One section, as you guys can see in this parallel circuit. But the rest of the sections of the lights, the rest of the columns, they still work. Well, why is that? It's because even though one of the sections is broken, right? One of the sections is broken, the electrons can still flow through other paths and light up the other sections, right? And so parallel definitely has a lot of advantages. But we are going to start simple. We are going to start with series circuits. It is a more simplest circuit to understand. Again, a series circuit really only has one path for electrons to flow. Now let's talk about voltage. And think about it this way. Right? Think about it this way. So let's say we have voltage here, right? So we have this dam. We're going to relate kind of electricity to water again. Let's say, for example, this dam, right? And you'll know that, well, on one side, you have a lot of water, right? You have a lot of water on one side. And well, what's happening is that this water is kind of go down to the side that has less water, as you guys can see in the image. And you can kind of relate this to a battery, right? So on one side of the battery, there's so many electrons. There's so many electrons, right? There are negative ions here. And while there are still protons, there's not as many of them, right? So you have a lot of electrons here. A lot of electrons. And what do all these electrons want to do? Well, they kind of want to force each other to move to the other side, move to the other side of the circuit, right? Because there's not as many electrons here. There's actually more protons than electrons. And because there are more protons than electrons on the other side, well, they're more likely to move to the other side, right? And we call this difference in, let's say, energy, right? This potential, this electric potential, we call this difference in potential difference. We call it voltage, right? There's a voltage difference here, right? And so the battery creates this voltage difference, allowing electrons being able to move these electrons, right? So again, if you kind of take a look at the bottom right hand GIF, right? If you take a look at the bottom right hand GIF, well, you'll see that the battery provides a certain amount of voltage to increase the energy. And as these electrons are moving through the light bulb, well, they kind of drop, right? They drop, and there's like something called a potential drop, right? There's a drop in energy because it took this amount of energy to kind of move these electrons. And as you now use that energy to move those electrons across the light bulb, your total energy, your remaining energy decreases, right? So So let's actually segue into what voltage actually is, or rather a simplistic analogy to what it is, right? So there's not a lot of electrons on one side, right? So we can say, well, that's 3 volts. And on the top side here, let's say, well, I have a voltage of 15 volts. And well, my potential difference here is 12 volts, right? That's my potential difference. That's the difference in energy in both points. And so up here, my total energy is 15 volts, right? And but as my electrons kind of go through a resistor, right, my voltage decreases. My voltage decreases. So let's say, well, now it decreases to 8 volts. So it took 7 volts to kind of of energy to kind of push these electrons through this resistor. And so now here across the second resistor, right? And so we will, let's say, I don't know, 4 volts, right? So it decreased 4 volts. So I have a voltage drop, a potential drop as it goes through the second resistor. And finally, well, it goes from 4 volts to 3 volts. And so my voltage here, my potential drop across each resistor is equal to my total voltage provided by the battery. Right, so my battery provides a voltage of 12 volts, and each resistor causes the voltage to drop, which we call a potential drop. But my total voltage is equal to the voltage across all 3 resistors, which is what you see at the bottom, that formula at the bottom, right? So you see that in series circuits right here on the reference table that your total voltage is really just equal to all the individual voltages combined. And again, that's really why we call it potential drop. There's a potential drop here, right? And so let's talk about electric current. All right. So let's have an example, right? Let's say you have a water pipe, right? So the huge tank of water, right? And it's going through a pipe. Right? So this pipe right here. And let's say there's an obstruction here, right? So there's an obstruction here that kind of lowers the amount of water that can flow through, right? So let's just color that in. And here, there's not as much obstruction, right? There's less obstruction. Right? So, and here there's just a really large opening in the pipe, right? So you can have a large opening right there. But as water is kind of going through this pipe, the water is getting limited by really the first obstruction, right? So there's not a lot of water that can kind of flow through that pipe. And as a result, well, what's the amount of water that can flow through the next obstructions? Well, very little as well, right? Because the other obstructions, other paths past the circuit, I mean, right, not circuit, but this first obstruction is really limited by the amount of water that's coming out. So my water current throughout the entire path here is the same. It doesn't matter how large this opening is, right, or how small it is. You're really limited by the smallest, rather the largest obstruction, because there's only there's so much amount of water that can kind of flow through this pipe after the first opening. And if you kind of relate that to circuits, right? If you kind of relate that to circuits, well, the resistor is the obstruction, and you kind of really limited the amount of electrons that can kind of flow through a resistor. You're kind of limited by whatever resistor is the strongest, right? And you can kind of think of electric current that way. So that's why my electric current in a series circuit is the same throughout. And so I is equal to I1 is equal to I2 is equal to I3. And resistance, my total resistance of my of my entire circuit really is equal to all the individual resistances combined. So the first resistor is really R1 and R2 is the second one and R3 is the third one. So my equivalent resistance is equal to all 3 of these resistors combined. Well, now how do we use Ohm's law? Right? How do we use Ohm's law in terms of a circuit? Because you're going to be doing that a lot. You're going to be doing that a lot. So when we're using Ohm's law, which is R is the V over I, right? So my total resistance, my equivalent resistance, is really just equal to my total voltage over my total current. But the total part of your current is unnecessary because, again, well, my current is the same throughout. So it doesn't really matter if I say my total current or my individual current, they're all the same. Or if I'm solving for the resistance of one object or the voltage of one object around the resistor, well, I'm going to do R1 is equal to V1 over my current. I'm never going to mix my formula. I'm not going to say, well, my total resistance is equal to my individual voltage over my current. I'm not going to mix total and individual. I have to use either all total or all individual. And so that's the biggest problem students have when really solving problems with series circuits. And so a student constructs a series circuit using, you have all this information here, right? There's a lamp, there's a resistor, and the circuit does not contain a voltmeter or ammeter, and when the circuit is operating, the total current throughout the circuit is 0.5 amperes. And so in the space, draw a diagram of the series circuit constructed to operate the lamp. Now you'll see all the symbols for your circuits right here. You see the battery, you see the resistor, and you see the lamp. Again, what the defining feature of a, the defining feature of a series circuit is, well, there's only one path for electrons to take. So I'm going to draw my battery, and really the short side is your negative side, and the long side is your positive side. I'm going to say this is my 12-volt battery because it says you have a 12-volt battery. I'm going to continue drawing my circuit. I'm going to draw my lamp here. So the lamp is kind of like a circle with a filament there. And then they say, well, then they have a resistor, right? An unknown resistor. You don't know what this resistor is. Could be a TV for all we care, but we don't really care in this situation. And so I'm going to finish my series circuit like that, right? There's only one path for electrons to take. This is a series circuit. Alternatively, you could really just also draw this, right? It doesn't really matter, right? So, and then you can proceed to draw your lamp, right? And you can do this. And again, guys, the defining feature of a series circuit is that you only have one path. There's only one path for your electrons to take. And so that's really the defining feature. And so now 6b says, right, 6b says, well, determine the equivalent resistance of the circuit. So we know R1 is 10 ohms. That's what the problem says. And the current running through the circuit is 0.5 amps. And so the resistor is R2, right? So this is R2. And they want to know, well, what is my equivalent resistance? Well, we can use the fact that Req is equal to R1 plus R2, right? Because that's what we talked about earlier. Or we can use Ohm's law, where Req is equal to my total voltage over my total current, which really is the same throughout the circuit. And we're going to use this because, again, we have voltage and we have I, and we're solving for Req. So here my total voltage is 12 volts over I, which is 0.5. And so Req right here is now 24 ohms. 24 ohms. And that is my equivalent resistance. And now the question wants you to determine, well, determine the resistance of the resistor, which is R2. But again, we know that in a series circuit, my total resistance is equal to all my individual resistances combined. And we have my total resistance, which is 24. And we know the resistance of resistor 1 of this lamp is 10. And so if we kind of subtract 10 on both sides, well, now we get 14 ohms is equal to R2. And that's the resistance across the resistor. Now we have 6D right here. the circuit has 4 ohm resistors, right? So you have 4 ohms for resistors connected together. So it's probably gonna look something like this, right? So that, maybe that. Yeah, I'm kind of just speed drawing this. And so that's a resistor, right? That's circuit A. And circuit B is going to be, we'll just have 2 resistors, right? And that's circuit B, right? So where circuit A has 4 resistors, circuit B only has 2. Now, the voltage of both of these batteries that are connected to these resistors is 24 volts. And the question wants you to compare, well, what is my total potential drop across this circuit? Again, as we discussed earlier when we were covering potential drop, the potential drop across each resistor might vary or might be different. But the question is asking you for your total potential drop, right? So the energy difference from this side of the battery and the other side of the battery. But they tell you what the energy difference is. Your voltage is 24 volts. Your potential drop is 24 volts. And so B also has a potential drop of 24 volts. So the answer here is the same. You're comparing the total potential drop, not the individual potential drop, but the total. Move on to 6E. Right, so you have 4 resistors here connected to a 12-volt source. And the question wants you to find out, well, what is your total current throughout this circuit? Now, again, when you're kind of looking for, when you're kind of solving for your total values, because we don't have my voltage across each resistor, right? We don't know what V1 is, V2, V3, etc. What we can do is we can get our total resistance instead, right? And my total resistance is really just, again, by the formula, is just all your individual resistances combined. And so really my equivalent resistance is going to be 10, 18, 24 ohms. And now all I do is substitute it. We know that my voltage is 12 volts. And so 12 is there, and then over I, and I is what we want to solve for. Multiply on both sides, 24I, 12 divided by 24. And my current here is 0.5 amps. And that's my answer. That's my total current. So we have this problem right here. So we have a 3 ohm resistor and a 6 ohm resistor connected in series. Right, so let me draw that for you. So you have a 3 ohm resistor and a 6 ohm resistor. So R1 is equal to 3.0 ohms. R2 is equal to 6.0 ohms. The current running through the circuit is 4 amps. And again, we know that the current throughout the series circuit is the same. And they want to know, well, what is the potential difference across the 6 ohm resistor? So V2, what is V2? But again, guys, we know that current is the same throughout the circuit. So when we do our individual ohms law, we do R2 is with a V2 over I. I is the same across each resistor. So we have 6 over V2 over I, which is 4 times 4 on both sides, and we get 24 volts, and that's going to be V2. If several resistors are connected in series in an electrical circuit, the potential difference across each circuit is what? So we know that my current is constant, right? My current is constant. It's the same throughout the circuit. So no matter what I do, I is going to remain constant. But if we're comparing R and V while I remains constant, well, what's the relationship here? What's the relationship between two things that are on the numerator? Well, the relationship between two quantities that are both on the numerator is directly proportional. So if my voltage increases by a certain proportion, then my resistance will also increase by a certain proportion as well. And so my answer here is C. It varies directly with the resistance of each resistor. And that's it, guys.